This is the final project presentation for Group 2. We're going to be presenting on alternative resistance fitness machine design analysis. Just a quick review of our table of contents. We'll take you through the introduction, a little bit of background as to why we're pursuing this particular project. Then we'll go through customer needs and functional requirements analysis, axiomatic design comparison, functional structure diagrams, bill of materials analysis, analysis for family products development, and then conclusion. All right, so just a little bit of background as to why we went down this particular project. We are analyzing an alternative design to a weightlifting machine, and going back through history, you look at weightlifting at its core, and there's been little evolution in weightlifting since it was basically introduced. You've got the core principle of picking weights up and putting them back down in an effort to increase size and muscle size, strength and muscle size. Right now, our particular design that we're looking at is a compact fitness machine, and that primarily revolves around a weight stack machine. So you've got a series of weights that you can select a different weight, and then it's connected to a series of pulleys. And as you can see in the photo, you pull on the different bands, and that creates the resistance necessary for increasing strength and muscle size, which is much smaller, more compact system than traditional weights. However, current weight stack machines are limited to one exercise, overly complicated when trying to incorporate many types of lifts, space hungry, and most importantly, they're still extraordinarily large. So the design that we're analyzing in particular is a solution to the size issue, and it involves a servomotor gearbox design. So our goal in this is to analyze the alternative resistance fitness machine utilizing this electromechanical design in lieu of a traditional weight stack. The basis of this, the design was sponsored by a company, Wahoo Fitness, and the design that came out of that is actually one of the projects for one of our group members for their senior design project. So the basics of the design is that it focuses around a servomotor gearbox consisting of three major components. You'll see those highlighted in the exploded view in both CAD and actually in the prototype model on the left side of the screen. You've got the retrofittable weight stack machine, which is at the very top of the screen, and then the actual new design consists of a servomotor gearbox assembly. You can see that highlighted with the yellow font on your left, and then also a custom spooling system with trolley and housing. You can see that highlighted in blue on your left. So taking this basic design, we're going to analyze it through the lens of axiomatic design and attempt to take this from a prototype and develop it into a fitness machine that is the basis of a family of products. So we're going to start by looking at customer needs and the functional requirements that are going to come from that. To start with all this, we need to take what the customer wants from the customer domain, the customer needs that they have defined in very nebulous terms, and translate that into something that engineers can actually work with. We need to take from the customer domain into the functional domain and develop tangible functional requirements that can be incorporated into design parameters. As we stated before, the project itself, the original project was commissioned by Wahoo Fitness, and so they provided the bulk of the raw data for the customer needs. And in terms of taking those customer needs and turning them into requirements, first had to elicit the requirements and then take that through a circular process of analyzing those requirements, creating specifications for those requirements, and in each step, feeding those outputs back into the initial elicitation. And from each one of those steps, we were able to determine functional requirements that would translate the customer needs into the functional domain. Of note, we had to come up with solution-neutral terms for our functional requirements that would not overly favor one design over another. Here, to continue the customer needs and functional requirements analysis, is a quality function deployment diagram, otherwise known as the house quality. The primary purpose of this diagram is to create to determine the correlation between customer needs and functionalized requirements. So if you take a look at the diagram, you'll see that the customer needs are listed there on the left side. From the previous slide, taking those customer needs and determining the functional requirements associated with them, those are then listed across the top of the diagram in orange. At the very top, you'll notice in the green, you'll have a correlation matrix that determines the relationship between the different functional requirements. And finally, across the bottom, you're going to have the design targets. And this is going to be the primary output from this QFD. And this is going to allow us to rank the functional requirements in terms of how important they are to the overall design. So we're primarily going to focus in on the correlation, the relationship matrix between the customer needs and the functional requirements. You'll notice that all of those inputs are in blue. So each of those weights is assigned a value based on 0, no correlation, 1, a minor correlation, 3, correlation, and a 9 is a strong correlation. Taking those values and then inputting them with the customer importance, which is a subjective measure, but is going to heavily factor into the individual importance of the functional requirements. You'll see down at the bottom with our design targets, you've got an absolute score, which is just the weights that were given to each functional requirement. And finally, taking into account the customer importance and the number of the score for each of the functional requirements, you'll see that a final score has been weighted and normalized and is produced at a 10. From those, the functions that are most important technically are listed there on the right side. And those are 1, compatibility with the standard pulley and weightlifting rack, 2, the force profile, 3, life cycle, 4, selectable resistance, 5, safety, 6, noise generation, and 7, size or system size limit. These functional requirements are particularly important because this is what's going to be used when we move into axiomatic design.
So now that the functional requirements have been depicted, we can derive the axiomatic design for the classic design with stack weights and the new design with a motor. More specifically, the independence axiom has been applied on both designs to show that the new design provides a better independence of the functional requirements. Let's break down the first design in terms of design parameters. We can notice that weight plates are the core, which are the core of the product, play a main role in almost all the functional requirements. The life cycle of the whole system depends on the type of the cable and the type of material that compose the weight plates. Force profile is correlated with the weight plates and their numbers. Adjustable resistance depends on the size of the weight plates. I mean, more tiny weights will allow a better adjustability. The noise generation depends on the number of weight plates that are lifted, the density of the material that compose the weight plates, and the contact surface. More surface will generate more noise. The safety is related to the contact surface. A good complementary between the weight plates will play a role, and the type of the cable. And the size limits depends on the weight plates. And finally, the compatibility to standard pulley system depend on the hook of the table and the hole in the weight plate. After having listed all the design parameters corresponding to the functional requirements, we build the axiomatic design matrix and observe that it is coupled.
As for the new design, since the weight stack is not part of the system anymore, most of the functional requirements are now independent. So if you take a look at the second and sixth functional requirements, on the previous design, both depend on the weight stack, but now they either depend on the reversibility of the motor rotation or on the size of the motor. Other functional requirements like the flexible resistance depend on the induced current. The noise generation will now depend on the magnetic field. So most of the design parameters are independent. And if we take a look at the new design matrix, it looks less heavy. By rearranging the rows, we can get a triangular matrix, meaning that we have a decoupled design. So using the axiomatic design, we prove that this new design provides a better independence on the functional requirements and hence is a more robust design.
Now let's move on to the functional description of our system. So we chose to use the IDEF0 diagram to characterize the functional structure of it. As the system is complex as a whole, we decided to divide it into four subsystems, which are the Boolean, the fault system, the servomotor part, the frame, and the user interface. So before going into the IDF0 in more detail, let's take a look at the overall layout of our system. So the lifting device that we're studying takes as input the user lifting force, which is the whole point of the study. It also takes the data storage selection because the customer actually has the ability to choose whether he wants the data to be stored on the cloud or not. There is also the desired weight that should be input and the AC power as incoming energy. The outputs are the performance metrics that are being displayed, the storage data on the network, so as I was talking before, on the cloud, and the actual resistance torque that the user experiences while he's training with the lifting device. So now let's take a look in the IDF0 in a little bit more details.
All right, so here's our IDF0 diagram, which is primarily used to help visualize the flow of inputs and outputs and the relationship between processes. And the inputs and outputs from the front function structure diagram shown in the previous slide can all be seen here. And in addition, we have multiple separate subsystems also represented. On the bottom, we have the data storage subsystem, which has three distinct steps. The AC power subsystem, again with three distinct steps, right above that. A controller where the user inputs the weight, and the physical lifting system at the top, which has 5 steps. And you can see those are all numbered. Each of those processes are numbered there. The design is kept simple by having primary outputs being displayed by the performance metrics being displayed at the end, and then the data being stored on the network. You can see those are the only 2 outputs from the entire IDF0 chart, making the design very simple.
The bill of materials was assembled to keep track of all the bought parts, raw materials, and material expenses. The original BOM was based on the public gym model, since other models currently planned varied from it by only one bought part. The main operations in producing the different models are essentially the same. The BOM and bill of operations were consolidated into a single bill of materials in operation. This facilitates estimating the material cost of producing one unit, which is about $2,862.63, with an additional $9.48 needed to machine the raw materials. There are a total of 31 unique bought parts across the 3 models, 28 of which are shared in common. There are 2 CNC machining operations and 5 assembly operations. No special tooling and fixturing are needed, and each of the 4 assemblies can be produced in parallel, then assembled with a frame. Here's the BOMO. It shows all the parts, sub-assemblies, and operations going through the manufacturing process. Of note are the motor and frame, which are contained within a red box. These are the variety parameters that vary with different models.
When creating a family of products, we first decided to look at where exactly weight machines were being utilized, and then see how our redesign could be used in these particular areas. We came away with 3 primary products, which include weight machines to be used in professional gyms, a home gym system, and then weight machines to be used in physical therapy spaces. The primary differences between these products are noted below, with professional gyms and home gyms needing a more powerful motor in order to help with strength building, while physical therapy machines are more for muscle recovery and therefore don't require a strong motor. Additionally, home gyms are usually contained within a smaller area and therefore need to use a frame that can consist of multiple machines into one frame, whereas professional gyms and physical therapy spaces can spread out their machines. What we particularly note, though, is that the spooling subsystem used is consistent throughout all the machines, as well as the electronics used to control the motor itself. A list of the particular specifications can be seen here, with, again, the differences being noted in how each product utilizes the motor and frame.
So here are our conclusions. After determining the customer needs and the functional requirements in the beginning of the project, we have determined that the alternative design using the motor is axiomatically superior to the standard weights. We're able to utilize design theory and bill of materials to create a family of products. However, throughout our design, we determined there were some deficiencies with the new design, and we determined there's still room for improvement axiomatically, as talked about previously. We can move closer to an uncoupled design. In addition, the torque generation from the motor is not entirely fluid, as the user moves the weight down. The motor is not able to respond quick enough and create a fluid force profile. In addition, we noticed that there's an excessive cost of the motor. However, this is still comparable to the cost of traditional weights, as weights we looked up are quite expensive. In addition, the cost savings by transporting just the motor as opposed to the traditional weight stack will be a lot lower. And lastly, retrofitting the existing frame leads to an increased cost, as the existing frame is essentially meant for traditional weights and has increased strength and other things like that. So if we could design or manufacture our own frame, we could seek to reduce costs even further. Thanks for listening to our talk.